So when we visualize like advanced clinical skills, I think the mind instinctively goes to the dramatic stuff, you know.
Oh, absolutely. Like placing a central line under pressure or, I don't know, running a code while all the alarms are blaring.
Right, exactly. Or interpreting some super chaotic EKG. We just expect the most dangerous moments in healthcare to be loud and highly technical.
Yeah, but the reality of clinical safety is actually a lot more insidious than that.
Totally.
I mean, one of the most high-stakes maneuvers a clinician makes doesn't even require a stethoscope.
Wait, really? What does it require then?
It literally just requires a keyboard, a charting system, and, well, a split-second moment of mathematical translation.
Wow, yeah. A simple dot on a screen or like a tiny percentage symbol on an IV bag can instantly become the most dangerous thing in the room.
Exactly. Which is why today we are plunging straight into the mechanics of fractions, decimals, and percent.
Yes, we are. And for those of you gearing up to conquer the TEAS and HESI nursing entrance exams, this deep dive is basically your operational blueprint.
Yeah, it's so critical to get this down.
Right. And the core premise we want to establish right away is that 3/4, 0.75, and 75% are not like distinct math concepts.
No, not at all. They are the exact same value, just wearing three different outfits, basically.
I love that. 3 different currencies. And mastering the fluent exchange rate between them is just a fundamental clinical skill.
It really is. And, categorizing these forms is actually a subject of pretty fierce debate in modern math education right now.
Really, a debate over basic percentages.
Yeah, I mean, they are all rational numbers, right? Meaning they express a part of a whole. But researchers are actively questioning whether percent should even exist as a standalone category in textbooks.
Wait, so they want to get rid of percents entirely?
Kind of. The argument is that a percent is really just a scaled display convention. It's just a relabeling of the fractions and decimals that students have, already mastered.
Oh, I see. So treating them as 3 totally isolated things just creates like massive cognitive friction for students?
Exactly. The modern push is to teach them as one continuous, flexible skill. You're just translating a single value across different formats to suit whatever calculation you're doing at that moment.
Okay, let's unpack this a bit.
Right.
Because if they represent the exact identical value, the obvious question is, why do we burden ourselves with 3 different formatting systems in the first place?
Right. Why make it so complicated?
Yeah. And to understand that, we have to look backward. These formats didn't just emerge from one cohesive theory or one person.
No, they definitely did not.
There are 3 completely isolated mathematical languages developed thousands of years apart on totally different continents, and they all just eventually crashed into a single modern math textbook.
It's basically a collision of ancient empires. So, fractions are the oldest surviving format. They are thoroughly documented in the Egyptian Rhind mathematical papyrus around 1650 BCE.
1650 BCE, that is wild.
Yeah, but the Egyptians used a really restrictive system of what we call unit fractions, so the numerator was strictly limited to 1.
Oh, so they only operated with things like 1/3, 1/5, 1/7.
Exactly. So to express a value like 3/5, an Egyptian scribe couldn't just, write a 3 over a 5.
What did they do then?
They had to break it down additively into 1/2 plus 1/10.
Oh man, that makes advanced engineering calculations sound unbelievably cumbersome.
Right. Every complex fraction turns into this huge, sprawling addition problem.
Which totally explains why the Babylonians took a completely different route. They went with a base 60, or sexagesimal, system.
Which was brilliant, honestly. The mechanics of base 60 are just perfect for fraction work.
Because 60 is a highly composite number, right?
Yes. It divides cleanly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30.
That is a lot of clean divisions.
It is, and that supreme divisibility is precisely why we are still tethered to Babylonian math today.
Oh, because of time. We carry that ancient engineering solution on our wrists every time we look at a clock with 60 minutes.
Yep. Or when we measure a circle with 360 degrees, base 10, on the other hand, only divides cleanly by 2 and 5.
Right. If you try to divide 10 by 3, you get a messy repeating decimal. So the Babylonians bypass that entirely.
Exactly. It's this unbroken mathematical inheritance designed specifically to avoid messy fractional divisions.
Oh, I love that. So then, centuries later, the decimal system emerges, and the historical credit for it is pretty deeply contested, right?
Oh, very contested. The Flemish mathematician Simon Stevin usually gets the Western glory for publishing a pamphlet in 1585.
Right, The Art of Tenths, I think it was called, aimed at standardizing calculations for merchants.
Yeah, but he was essentially running a PR campaign for an architecture that had been thriving for centuries in the Islamic Golden Age.
Wait, really? So it was already being used long before that.
Oh, absolutely. Decimal fractions were systematically employed by the Persian mathematician Jamshid al-Kashi in 1427.
Wow, so way earlier.
And historians track the foundational mechanics back even further to the Syrian mathematician al-Qudsi around 952 CE.
That is fascinating.
And honestly, long before that, Chinese mathematicians were utilizing sophisticated place value systems that function similarly.
So decimals are really a phenomenon of independent, parallel discovery across all these diverse traditions,
Mhm.
born out of the necessity for, like, astronomical and engineering precision.
Exactly. But percents, on the other hand, they strip away all the pure mathematics and the astronomy.
Right. The origin of the percent is entirely driven by politics and tax collection.
Always comes back to taxes, doesn't it?
It really does. The Roman Emperor Augustus established the centessa rerum venalium, which was a strict 1% tax on goods sold at auction.
So calculating in hundredths basically became the mandatory baseline of daily Roman commerce.
Yeah, and the visual symbol we use today has such a fascinating physical evolution.
Oh, the scribbling thing, right?
Yes. Medieval Italian merchants would scribble the phrase percento on ledgers. And over generations of rapid, sloppy bookkeeping, it compressed into a P and a C with a little circle.
And then that eventually degraded entirely into the diagonal line and two circles that we recognize as the modern percent sign.
Exactly. So learning this math is basically like dealing with three different ancient languages. You've got ancient Egyptian fractions, Middle Eastern engineering for decimals, and Roman tax law for percents.
And when you sit down for the TEAS or HESI exam, you are acting as the translator between all three of them under strict time pressure.
Right, trying to force all these historical ghosts to communicate with each other on a nursing exam.
Which is why the exams are testing your cognitive processing speed in managing those translations.
So let's break down the mechanics of moving between these currencies. Translating a fraction to a decimal requires basic division, but, like, time is your enemy on these exams.
It really is. Every second counts.
So there is a specific strategic advantage in rote memorization here, especially for the eighths family. 1/8, 3/8, 5/8, 7/8.
Yeah, you have to know those cold. Those specific fractions appear relentlessly in nursing dosage calculations, and they terminate in 3 decimal places.
Right, so if you pause to manually divide 3 by 8 to get 0.375, you are bleeding precious time.
Exactly. Recognizing instantly that 5/8 is 0.625 allows you to bypass the calculation entirely and move straight into the clinical application.
Okay, so to exchange that decimal into a percent currency, you just multiply by 100, which shifts the decimal point 2 places to the right and attach the percent symbol.
Yep. So 0.375 becomes 37.5%.
And reversing the process simply means placing the percent value over a denominator of 100 and simplifying the fraction to its lowest terms.
Super straightforward once you get the hang of it.
So let's look at a concrete clinical example of this. Total body water constitutes roughly 60% of an adult's body weight, right?
Right. So if a patient weighs 70 kilograms, we need to quantify that fluid volume.
But operating directly with the integer 60 will give you an absurd, biologically impossible result.
Yeah, you'd get 4,200 kilograms, which is obviously wrong. You must translate the currency.
So 60% converts to the decimal 0.60.
Exactly. And multiplying the 70 kilogram mass by 0.60 yields 42 kilograms.
And since the density of water is roughly 1 kilogram per liter, we are looking at an internal volume of approximately 42 liters of water.
Spot on. And drug labels demand the exact same fluency. Like when you pull a vial of 2% lidocaine, the label is hiding a ratio in plain sight.
Oh, I see where you're going with this. 2% literally translates to 2 grams of the active drug suspended in 100 milliliters of solution.
Right. And to execute any downstream dosage math, you have to extract that fraction and convert it to a working decimal.
So 0.02 grams per milliliter. And without that initial translation, you basically can't even start the medication calculation.
You really can't. But this is where we run into a massive cognitive hazard.
Okay, let's hear it.
There is a powerful temptation, especially under the artificial time pressure of a standardized test, to just like take a fraction, like 1/3, round it to 0.33, call it 33%, and move on.
I mean, if I'm on the clock, Why can't I just do that? Isn't close enough? Close enough?
Well, close enough is a catastrophic failure in pharmacology. This is what we call the repeating decimal trap.
The repeating decimal trap. Because 1/3 is exactly 0.333 repeating forever.
Exactly. Truncating that early to 33% injects a tiny mathematical error into your formula.
But it's so small. Does it really matter?
If you are calculating a single isolated value, maybe that error remains negligible. But dosage calculations are rarely isolated values. They are multivariable sequential operations.
Right, because you factor in patient weight, the drug concentration, infusion time, the drip chamber drop factors, all of it.
Exactly. So if you introduce a rounding error in step 1, that error compounds exponentially through every subsequent multiplication and division.
Wow. So by the time you reach the final infusion rate at, like, step 5, your truncated decimal has shifted the final drug volume by a measurable, potentially dangerous amount.
Yes. Mathematical precision must be preserved across the entire equation. You only round once, and you do it at the very end, to the final resulting number.
That makes so much sense. So the stakes here transition pretty rapidly from losing a point on a multiple-choice test to causing active harm on a hospital floor.
They really do. A misplaced decimal on the TEAS costs points, but in the hospital, it literally costs lives.
And the way human psychology interacts with numeric displays is heavily flawed, which the clinical environment exposes mercilessly.
Yeah, human psychology really betrays us here.
The tragic case of Emily Jerry in 2006 is a brutal demonstration of this reality.
It is so heartbreaking. She was a 2-year-old girl undergoing chemotherapy in Ohio, right?
Yeah. And a pharmacy technician formulated her IV bag with a massively concentrated sodium chloride solution, completely miscalculating the required dilution.
Right. The technician utilized a 23.4% hypertonic saline solution instead of the standard 0.9% normal saline that was ordered.
It's just a horrifying mistake. The mathematical failure to comprehend and convert those concentration percentages resulted in a lethal overdose of sodium.
Which led directly to her death. It actually prompted sweeping legislative changes in pharmacy oversight, especially in Ohio.
And the underlying failure mechanism there was the inability to safely process concentration variables under systemic pressure.
Exactly, which is why, to forcefully mitigate these visual processing failures, the Institute for Safe Medication Practices, the ISMP, enforces really draconian rules regarding decimal notation.
The zero-tolerance reality, like the trailing zero, is universally banned.
Yeah, absolutely banned.
If a physician orders 5 milligrams of a medication, writing 5.0 is a critical safety violation.
And this raises an important question about why people do it in the first place. The psychology behind the trailing zero is deceptive.
How so?
Well, a clinician writes 5.0 because it feels authoritative. It projects this aura of scientific precision.
Oh, I see. Our brains want to read it as safer or more precise.
Right. But in a fast-paced environment, reading through a glowing screen or quickly scanning a chart, the decimal point just vanishes into visual noise.
So the next nurse on shift sees a 50 instead of a 5.
Exactly. You have just authorized a 10-fold overdose simply because you wanted the number to look precise.
That is terrifying. And the inverse rule is just as strict. The leading zero is mandatory.
Always.
So a half-milligram dose must be charted as 0.5. Writing 0.5 with no zero in front guarantees that eventually someone will miss the isolated dot, read it as a whole number 5, and deliver another 10-fold overdose.
A single typographic dot represents an order of magnitude shift in physiological impact. It's wild to think about.
It really is. And this visual deception isn't just a clinical phenomenon, is it?
No, it's embedded in the very nature of decimal notation itself. Consider the classic mathematical debate over repeating nines.
Oh, right. Does 0.999, extending into infinity, actually equal 1?
Right. Intuition screams that it has to be infinitesimally smaller than 1 because it starts with a 0.
But the mechanics prove otherwise. Rigorously, mathematically, yes, they are equal.
Do you want to walk through the proof?
Yeah, let's do it. So if you take the fraction 1/3, we know that it equals 0.333 repeating forever.
Right.
If you multiply 1/3 by 3, you get 3/3, which is exactly 1.
Okay, tracking.
And if you do the same thing to the decimal equivalent, multiply 0.333 repeating by 3, you get 0.999 repeating.
Exactly. Therefore, 0.9 repeating and the integer 1 are the exact same numeric value.
It's crazy. That proof just shatters our reliance on visual intuition. It demonstrates mathematically that the exact same real number can possess two wildly different decimal representations.
Which just proves you cannot trust your immediate visual processing when evaluating numeric weight.
Right. And since our visual intuition is compromised, we really have to consciously rewire how we approach the common mental traps engineered into these nursing exams.
Yeah, you have to be so careful.
The most pervasive trap is the size illusion surrounding fractions. The human brain naturally correlates larger digits with larger values.
It's so easy to fall for. A student sees a denominator of 8 and a denominator of 4 and instinctively assumes 1/8 must carry more weight than 1/4 because 8 is bigger than 4.
But we have to isolate the mechanical function of the denominator. When numerators are identical, the relationship to the denominator is strictly inversely proportional.
Right. The denominator dictates how many distinct pieces the original whole has been fractured into.
So fracturing a standard volume into 8 separate compartments yields significantly smaller individual units than fracturing that same volume into 4.
Exactly. 1/8 is smaller than 1/4. And that exact same cognitive failure happens with decimals, and test writers love to exploit it.
Oh, definitely. Like when comparing 0.45 and 0.5, the brain locks onto the 45, recognizes it as a larger integer than 5, and selects 0.45 as the larger value.
It's basically a failure to align place values. 0.5 is functionally 0.50.
In 50 hundredths definitively outweighs 45 hundredths.
Right.
Here's where it gets really interesting if we use the currency metaphor. 0.45 is basically a handful of 45 pennies. 0.5 is 5 dimes.
That's a great way to put it.
Having a longer string of digits, like a physically larger pile of coins, does not equate to a higher intrinsic value. You must evaluate the denomination of the currency, not just the volume of the digits.
Spot on. And another deeply ingrained fallacy is the percent ceiling.
Oh, the idea that percentages can't go above 100%.
Exactly. We are conditioned to view 100% as the absolute maximum capacity of a system. But functionally, a percent is merely a comparative ratio against a baseline of 100. It is not an upper limit.
Right, like a patient's heart rate can escalate by 150% during a physiological crisis. Or a trauma center can operate at 120% of its licensed bed capacity.
It simply indicates a value exceeding the initial reference point.
And then there is the trap of successive percentages, which requires an understanding of a shrinking mathematical base.
This one trips up so many people.
Say a pharmaceutical supplier offers a 20% discount on a $100 vial and later applies an additional 10% discount. The total reduction is not 30%.
No, it's not. The 20% reduction drops the baseline cost to $80.
Right.
Then the subsequent 10% discount is applied exclusively to that new shrinking base of $80.
Ah, okay. So 10% of 80 is $8. Subtracting that yields a final cost of $72.
Exactly. A flat 30% discount right off the bat would have driven the price down to $70, not $72.
And that mathematical drift occurs constantly in the clinic, right? Like when interpreting sequential percentage drops in a patient's lab values over consecutive days.
Absolutely. The base shrinks every day. And honestly, if we connect this to the bigger picture, navigating these systems with fluency dictates how you interface with reality well beyond the confines of a testing center.
It acts as the ultimate filter for processing data.
It's essentially the ultimate BS detector for modern adult life.
Take the framing of health statistics regarding absolute versus relative risk in the news.
Oh, this is a classic.
If a prevalent disease affects 2% of a demographic and a newly developed drug reduces that incidence rate to 1%, a headline will scream, "Treatment cuts disease risk in half."
And the math in that headline is technically valid, right? A drop from 2 to 1 is a 50% relative reduction.
But the absolute reduction in risk is a microscopic 1 percentage point.
Exactly. Without the operational fluency to instantly separate relative percentage drops from absolute baseline shifts, clinicians and patients alike are entirely at the mercy of manipulated statistical narratives.
Right. And this foundational literacy is what unlocks the more advanced architecture of nursing math. You cannot execute dimensional analysis, the factor label method, without seamlessly swapping fractions and decimals to cancel out intersecting units of measure.
You really can't. It dictates rate calculations, like programming an infusion pump to deliver a precise number of milliliters per hour.
It even governs how we interpret ratio strength notation, like the 1:1,000 epinephrine used in anaphylaxis protocols.
Yeah, because that ratio is simply another fraction in disguise. 1 gram of epinephrine over 1,000 milliliters of solvent.
So testing bodies heavily weight these conversions because this specific mathematical agility is the proxy they use to determine if a candidate possesses the cognitive discipline to safely manipulate variables under stress.
Exactly. They need to know you can handle it.
All right, let's distill the operational protocols from this deep dive into 5 core mandates you need to carry into the exam.
Let's do it.
First, fractions, decimals, and percents are identical values operating in different currencies. Do not waste time recalculating from scratch. Simply execute the exchange rate.
Perfect.
Second, the ISNP guidelines are absolute. The omission of a leading zero or the addition of a trailing zero is a tenfold medication error waiting to happen. Write 0.5, never 0.5 and never 5.0.
Crucial.
Third, a percent is a ratio per 100, not a biological or systemic ceiling. Values frequently and naturally exceed 100%.
Yep, the ceiling is a myth.
Fourth, decimal length is an optical illusion. Always align place values. A longer string of digits has zero correlation with the actual magnitude of the number.
Align those decimals, people.
And fifth, preserve mathematical precision until the end. Round once at the very end to avoid compounding errors that shift clinical outcomes.
Honestly, internalizing the mechanics behind those 5 principles shifts your approach from simply memorizing rules to genuinely understanding the architecture of the equations.
I completely agree. Now, before we wrap up, I want to leave you with one final, slightly provocative thought to mull over.
Ooh, all right.
We spent this entire time optimizing how to translate numbers perfectly into these 3 systems. But earlier, we briefly touched on the fact that the natural world routinely produces values that break all 3 formats.
Oh, you're talking about irrational numbers?
Yes. Think about pi. Values that continue infinitely without ever settling into a repeating pattern.
Never terminating, never repeating.
Because pi cannot be written as a simple unit fraction, and because it never forms a clean, predictable decimal, you physically cannot write its exact perfect percentage.
Wow. Yeah, you literally can't.
How fascinating is it that something as structurally basic as the geometry of a perfect circle relies on a value that completely defies ancient Egyptian fraction mechanics, Babylonian engineering, and modern decimal notation?
It's kind of humbling. It demonstrates that mathematics is just an ongoing human attempt to model reality, and those models always have boundaries.
Right. We built these elaborate systems to control and calculate our environment, and the universe still generates absolute realities that slip right through the cracks of all 3 historical systems.
That is wild to think about.
Which returns us perfectly to that simple silent dot on a clinical chart. It is our best attempt to translate reality into a format we can act upon. Mastering that translation doesn't just earn you a passing score, it ensures the safety of every patient relying on your precision.
Absolutely.
Thank you so much for joining us on this deep dive. Keep grinding on that exam prep, trust the mechanics of the math, and keep pushing yourself to be brilliantly well-informed. Catch you next time.